1 lucky guy or gal, 3 eligible craters. Can a relationship be struck up? Find out this episode of Crater Dating. Crater dating is a concept, it's kind of cool, that we can use in planetary astronomy. The way it works is that we think that over the course of a long enough time, several 100 million years or longer, that the rate at which things in a certain area, like, say, the inner solar system, for instance, the rate at which they get hit by asteroids and comets and stuff is pretty consistent. And so if they're getting hit at a consistent rate, which we think they roughly are, then by looking at some area, in the inner solar system, for instance, like the moon or Mars or Mercury, anything like that, and by counting the number of craters and the number of craters of different sizes, that we can use that to get an idea of how old that area is. The surface that all those craters are hitting, we can learn about how old it is based on how many craters have hit it. And so the assignment associated with this week has to do with crater dating. You're going to be getting 2 pictures of different areas of Mars, and you're going to be asked to date them by looking at the craters. Now, the assignment asks you to count the craters yourself, but I think that would be a bad use of your time. I think that would just take too long, and it would be frustrating, and it'd be hard to tell which craters fall into which size categories, So actually, I'm just going to provide you the amount of craters in the 2 images. But then you are going to use math described in the assignment to convert them to a standard. Because, basically, the 2 images are of different amounts of Mars. One of them is about 812,000 square kilometers, and the other one's about 774,000 square kilometers. And to compare them with a graph and with things that we already know from, the Apollo mission, for instance, we were able to get really accurate datings on moon rocks. And so we were able to use that as a good, to effectively make comparisons between different surfaces in the solar system. But in order to make that comparison, we need to think about the number of craters in 1,000,000 square kilometers instead of 800,000 or whatever. So you're going to, multiply the number of craters that are actually in the image, which again, I'm going to give to you by a ratio of, say, 1,000,000 over 800,000, 812-some thousand, in the case of the 812,000 kilometer square image, to kind of say, okay, if there are this many in 812,000 square kilometers, there's probably going to be about this many in 1,000,000 square kilometers, right? And so you're going to do that for the 2 images, using all the numbers I give you, and then doing a ratio to figure out how many would be in 1,000,000 square kilometers. And then you can plot them on the plot that is present here. But this plot's a little bit unusual looking. It's a logarithmic plot. And logarithmic plots are a little different than what you're probably used to, but here's basically how they work. So I'll start with a normal graph. You've got a y-axis and an x-axis. And we'll say that maybe on the x-axis, let's say this is 1, and then you've got 2, 3, 4, etc. The idea here is that as you move one space to the right, that's like adding 1. And moving one space to the left is like subtracting 1. And of course you can do that on the y-axis too. So this is like a normal plot. But a logarithmic plot, a logarithmic graph, is a little bit different. It would look something like this. So maybe we have 1, 10, 100, 1,000, and so on. Here, instead of moving to the right one being adding 1, moving to the right one is multiplying by 10. And by the same token, moving to the left one space is dividing by 10. So, pretty similar, a little different. And in the case of this logarithmic plot that's on the thing, it has a thing where you'll look at the scale. In this one, the logarithmic plot's on the y-axis instead of the x-axis like I've drawn here, but there's no difference really. You'll see something like if this is the 10 and here's the 100, you'll see these smaller lines between them. And the purpose of these lines is to let you plot it more accurately, but they're a little weird because they start out pretty spread apart like this, but then they start getting more bunched together as you get closer to the next thing. And the way that you read these little lines is they're like steps of 10, but within the range of like the order that you're thinking of. So like this would be 20, this would be 30, 40, 50, 60, etc. up to 100. But then in the space between 100 and 1,000, this would be 200, 300, 400, 500, and so on, up to 1,000. So that's how you use that. Now this plot that you're seeing also has these big diagonal lines. I'll show it to you. It's got these diagonal lines on it. What that means, those aren't like an axis of the graph or anything. What those mean is basically, so this is a thing where you plot the crater diameter in kilometers on the x-axis and the number of craters per million square kilometers of that size on the y-axis. So like for instance, if you're looking at 7-kilometer diameter craters and you have 20 of them, then you'd go 7 and then here's 10, so that would be 20. So you'd plot a point right there as an example. Now these diagonal lines are basically, we've kind of done the math, we've done some comparisons, and each of these lines represents an age in billions of years. So this bottom diagonal line down here you can see is labeled 0.7. So that's 0.7 billion years, or 700 million years. Here's like 2 billion, 3 billion, 3.5 billion, 3.7 billion, 4 billion, 4.4 billion. And basically what these lines mean is we think, if we look at a surface that's 1 million square kilometers, and we know that it's a certain age, like say 3 billion years old, then we would expect that if we were to plot these crater values, if we were to look at the craters and count them up and then plot them, that it would get a line that looks something like the 3 line. Not exactly like the 3 line, but something pretty close. So that's what these mean. They're like guesses, like really well-educated guesses for what the lines of surfaces of various ages might approximately look like. And you're going to be making 2 lines. The northern hemisphere points are going to get 1 line, and the southern hemisphere points are going to get a different line, because the two surfaces the section of the northern hemisphere and the section of the southern hemisphere that you're looking at might be different ages. So you got to give them different lines. And then by kind of looking at the lines that you've made, you're going to compare them to these lines to kind of make a rough guess for roughly how old you think these surfaces are. For instance, if I get a line that's between 4.0, the 4.0 line and the 3.7 line, so it's something like this, I can maybe guess that the age of that's going to be somewhere between 4.0 and 3.7 billion years, something like that. So that's basically what you're doing there. And again, I'm going to give you I'm just going to give you the number of craters in these images on Canvas in the assignment. But you're going to have to do the math to convert that to the number in a million square kilometers. And then it's got some questions about it. I'm going to specifically talk about number 4, because 4 is a tough question. I got a lot of questions about it in class, so I want to go over it in here specifically to make sure that the people who missed class can still understand 4. So 4 says, consider these 2 facts. Sorry. A, the Earth has been hit by as many impactors as the Moon and Mars. This ties into what I was saying earlier about how anywhere in the inner solar system, we think the amount is pretty consistent, right? Earth, the Moon, Mars, Mercury, we think that for a certain amount of surface area on any of them, they're going to get hit by about the same number of meteors over the same amount of time. Stuff like that. And then it says the state of Oklahoma has a total land area of about 181,000 kilometers. And it wants you to calculate how many 5-kilometer sized craters have been formed in Oklahoma over the last 4 billion years. This question is tough, it has a lot of moving parts, but here basically is how you're going to want to approach it. It says, how many 5-kilometer diameter craters have formed over the last 4 billion years? So you can look at this plot, and you can look at your 4 billion year line. If you're thinking that Oklahoma is like a 4 billion year old surface, you can use this line to make a pretty good guess of how many craters it should have of various sizes. So we're looking for 5-kilometer diameter, so we can go up and see where it meets the 4 billion line. It meets it there. You can count that out, it's about 500. And so now, but you have to remember, that's not your answer, because that's the number of craters per 1,000,000 square kilometers. So you can do a pretty good guess that there would be about 500 in 1,000,000 square kilometers on Earth, but Oklahoma is only like 180,000 square kilometers. So again, you're going to have to make a ratio, like you did in the first part, to say, if there are this many in 1,000,000 square kilometers, I bet there are going to be about this many in 181,000, right? But you have to be careful to not use the same exact formula for the ratio that you used in this part, because in there you were taking a smaller amount of area and trying to extrapolate how many craters would be in a bigger area. And so you're going to be multiplying it by a fraction that's bigger than 1, which is going to make the number bigger. But here, you're starting with a bigger area and trying to guess how many would be in a smaller area. So you're going to want to multiply it by a fraction that's smaller than 1, which is going to make your number smaller. So make sure you do that, and with that, I think you can do number 4. And then number 5, which kind of builds on 4, it says, currently the state of Oklahoma has 0 5-kilometer impact craters. What happened to them? And so you can give some of your ideas for what happened to them. There are a few things. You might be able to look to my tectonic plates lecture for some hints as to what happened to them. One thing that's pretty well known is that the Earth's atmosphere puts a lot of friction on meteors. It burns them up. So a lot of meteors burn up in the atmosphere or sort of explode before they can even hit the ground. So they aren't forming craters that way. So that's one thing. Another thing is like volcanoes. Like I said, lava can fill in a crater. There aren't any volcanoes in Oklahoma, so that can't explain Oklahoma's. But somewhere else, volcanoes are a good example. I'm not going to give you all the possibilities, but those are a couple. And then there's also like erosion from like the wind and water and stuff can get rid of volcanoes on Earth. I'm not going to give you all of them, but those are just a few starting points to help you kind of start thinking about that question. So yeah, with this in mind, go ahead and work on this assignment, and feel free to email me if you have any other questions. With that, I think that about wraps this up.